In this video, I'm going to talk about the Fermat's theorem for extreme values. So this is how it goes. Let's say f is a function. F is a function that has local extreme values or local maximum or minimum values. Local max or mean values at some point, let's call it A. And also if f prime exists at that point, f prime of A exists, then it must be the case that f prime of A is equal to 0. Let me show it how it works. Let's consider the max case first, and then similarly we could derive the minimum case. So we are going to consider the max. So let's say f of A is a local maximum. That means we could find a neighborhood around A, okay, some neighborhood around A where any value we take in that neighborhood is going to be less than or equal to f of A. That means any value of x that we take in that open interval, that f of x is going to be less than or equal to f of A. So that means what we could say is this. We somehow want to introduce these derivatives. So we could remind ourselves of the definition of derivative, which is limit h approaches 0, f of x plus h minus f of x divided by h. That's the definition of derivative, right? Or f prime of x. So around this point A, I could find some value h, right? So such that, so let's say f of A plus h, okay? Now remember, it's a local maximum at A, so this must be less than or equal to f of A. Or equivalently, I could subtract, and I could say f of A plus h minus f of A is less than equal to 0. Now this h that I have introduced, if it's positive, we are going to be talking about the right side. If h is negative, then we are going to be talking about the left hand side. If it's positive, we are approaching the point A from the positive side. If h is negative, we are approaching the point A from the negative side. So coming from this side versus this side. Now let me go ahead and do some algebra here. I'm going to divide both sides of this by let's say h. I'm assuming h greater than 0, positive case. If I'm dividing by positive number, that's not going to change anything. So this gives me the following: f of A plus h, f of A plus h minus f of A divided by h is less than equal to 0 divided by h is 0. Now you can see this kind of looks like the derivative. You can guess already that I'm going to take limit of this as h approaches 0. Now remember, when h is positive, we are approaching the point A from the right side. So I'm going to apply limit h approaches 0 from the positive side, f of A plus h minus f of A divided by h is less than equal to limit h approaches 0 from the positive side 0, but this is constant, so nothing is going to happen here. So I'm going to have limit h approaches 0 from the positive side, f of A plus h minus f of A divided by h must be less than or equal to 0. At this point, I'm going to use the fact that the derivative exists, right, at point A, if the derivative exists at point A for f, the function f, then left limit and right limit must be the same. So it must be the case f prime of A is equal to limit h approaches 0 f of A plus h minus f of A divided by h. By the way, this is just the regular limit. Look, 0, not 0 plus. Must be equal to limit h approaches 0 from the positive side. So this is this one. The f of A plus h minus f of A, all of it divided by h, must be less than equal to 0. Now, just by looking at this chain of statements, you can see that f prime of A must be less than or equal to 0, because f prime of A is the same as this, which is equal to this, but this is less than or equal to 0. So it must be the case f prime of A is less than or equal to 0. So remember this statement, we will need it later. Now let's go ahead and divide this expression f of A plus h. So f of A plus h minus f of A. I'm going to put 0 here. So now in this case I have divided by positive h. But what if my h is negative? That means I'm going from the left hand side. So h less than 0. Then what's going to happen when I divide by h? This inequality is going to flip. So that means this is going to be greater than or equal to 0. So that's the key observation or key difference. So when I'm dividing an inequality or multiplying an inequality by a negative number, that reverses or switches the inequality. Now, this must be the same as limit h approaches 0 from the negative side. And let me just do a little bit of erasing here. Okay, is the same as limit h approaches 0 from the negative side 0. But this guy is nothing but 0, right? Limit, because 0 is not dependent on h, so this is 0. So now if I were to rewrite it, kind of extend it just to save time, I'm going to say this is the same as limit h approaches 0 f of A plus h minus f of A divided by h. This is equal to f prime of A. Because the derivative exists at point A, left limit and right limit must be equal, and it must be equal to the actual limit. That means the derivative. So this sequence of statements, if I put it next to each other, which I did here, this says this is equal to this, which is equal to this, which is greater than or equal to 0. Greater than or equal to 0. So that is to say, I just concluded that f prime of A is greater than or equal to 0. So I'm going to put it in a box here. And now look, this statement says f prime of A is less than or equal to 0. And this statement says f prime of A is greater than or equal to 0. Or equivalently, derivative of function f at point A is less than or equal to 0. Derivative of function f at point A is greater than or equal to 0. For both of these statements to be true, it must be the case that f prime of A is equal to 0. If that is the case only, that's when this statement will be true as well as this statement will be true. Therefore, I just concluded, or I just showed, that derivative of the function, if it exists at a local maximum, is 0. And similarly, with similar argument, you can show that the derivative at a local minimum is also 0. So we showed derivative at a local maximum is 0, and using similar argument we can show that derivative at a local minimum is 0 as well. However, there's a little caution that I want to use here. Okay, so very important. You cannot be assuming that if f prime of a is equal to 0, that means that the point A is a local max / mean. Okay, that, by the way, is incorrect. It doesn't go the other way around. That means if it is a local maximum or minimum and the derivative exists, that's when f prime of a is going to be equal to 0. However, you cannot switch the argument and say, oh yeah, I have a function, I have gotten a derivative to be 0 at some point. That doesn't mean that it will be a local maximum or minimum. There are a couple of examples. One classic example is the x cube function, okay, which kind of looks like this. At this point, by the way, the derivative is 0. You can see the slope of the tangent line is going to be 0. Okay, derivative f prime of, let's say, point A, f prime of A is equal to 0. However, this point is neither maximum nor minimum. If you go to the right, it increases. If you go to the left, it decreases. Okay? So it's neither max nor mean. Another classic example is the absolute value function. So if your y is equal to f of x is equal to absolute value of x, then what happens? How does it look like? It's a v-shaped function, right? Going through the origin. Now, this, by the way, is a minimum for this function. However, at this point, as we know from our prior knowledge, the derivative doesn't exist. Okay, f prime does not exist. So the reason I use these examples is to make sure that you just don't assume the converse of the argument. If it's a local max or mean and derivative exists, then the derivative should be 0. Automatically do not assume that, oh, okay, the derivative is 0 means that it's a local max or mean. The statement other way does not hold true. I hope that this discussion was helpful. Thank you very much.